Hello ladies and gentlemen, and welcome to another session of Advanced Seismic Design of Structures CG0061. I'm Arash, and today we're going to talk about performance-based earthquake engineering PBEE, and we'll see how this new methodology is affecting the seismic design and generally earthquake engineering. These are some outlines of today, so we're going to talk a little bit about the history and why we needed such thing. Then we will talk about the methodology that we use in performance-based earthquake engineering. Then we'll see some cases that we have implemented and how we implement the performance-based earthquake engineering. Then we'll switch on to performance-based seismic design, which is based on PBEE, and we will compare it to code-based seismic design that we were always using based on Eurocode 8 or any other code like ASCII. And at the end, we'll see some sample projects, very simple, on how performance-based seismic design have been implemented in designing new buildings. So around year 2000, a new vision came out that we need to have a transformation of our design and assessment, and we want to combine these two. So the vision for performance-based earthquake engineering was started. Generally, in a traditional approach, the seismic hazard that we consider is not very scientific. We just consider response spectrum. We don't look at the specific location. We just simplify that complex earthquake and complex hazard to a simple, smooth curve of elastic response spectrum that the code has given us. So we trust it, although it is scientifically approved, but it's not very representative of the location that we're going to have our building. Then we do indirect design approaches. By this I mean like we're using behavior factor to represent the entire ductility of my structure. Is that really correct? My structure is a steel structure. Why don't I design it and consider it as that instead of just using a behavior factor which is applicable to all types of steel structures, all types of concrete structures, all type of masonry structures? For sure, that's very much simplification. So it's not very direct approach of design. And then undefined and uncertain outcomes. Imagine you're the stakeholder, you're the owner of the building. Someone has designed the building for you, and you know it's an earthquake prone area. For example, let's say we're building our building in north of India, and we ask the designer that what will happen to my building if a magnitude 7 earthquake happens a few kilometers away from my building. What is the real answer to this question? Can anyone have a certain answer to this? So based on the traditional codes, we never worked with that magnitude. We just trusted that the hazard is whatever the response spectrum tells us, and we just approved it based on some behavior factors, and we extracted some acceleration, then we got the base shear, and then we just distributed among the height of my building. Does that tell me how and in what sense my building will perform under magnitude 7? Will my building collapse, or will it be safe? And remember this, the stakeholder or the owner of the building has no idea what intensity measure is, what attenuation relationship is. It just has heard from the news that the earthquake is measured with a magnitude of Richter or moment magnitude, something like that. So the traditional approach has these problems. It's not as clear as it should be. Now, the performance-based approach tries its best to have a scientifically defined seismic hazard. So we do the probabilistic seismic hazard assessment, PSHA. We know exactly at whatever location you give me, lat and lon, I can tell you what is the peak ground acceleration expected with a good percentage in any coming return period for the lifetime of your building. I can even move further and I can tell you what is the spectral acceleration according to the initial or the fundamental period of your structure. What is the acceleration at that point? we go to direct design approaches in performance-based design. So we don't simply design the building based on its elasticity and just use some behavior factor to consider its nonlinearity. We actually model the building with sophisticated software. We apply real earthquakes instead of representative lateral forces, and we really see what is the behavior of the building under different conditions, as we will discuss it in more details further. And based on this, if I have a real income from my earthquake, if I have a good representative of my building based on the nonlinear models that I'm creating, and I get a good performance or outcome from my building, I can really define the outcomes with a probability. So I can tell it that if an earthquake of magnitude 7 happens in this location with this distance, I can simply predict that the acceleration which will be applied to my building, for example, will be 1g. Under 1g, with such similar conditions, my building will perform in an acceptable way, in a way that, okay, only minor damage will happen to some of your components, or unfortunately your building will go under extensive damage and it might collapse. So the client knows exactly what they're dealing with. So that is the main differences. The traditional approaches are a little bit vague. They're not extremely scientific because they don't bring probability into it. Performance-based approaches are more advanced. They bring probability in it. They have the probability of the hazard, so it considers all possible scenarios, as well as we directly design the building. What we really want to be constructed, we model it properly and we see the behavior. Having these two, I can convince my client or stakeholder that if such an event happens, this is how my building will behave. If a bigger event happens, there is a chance that your building will collapse. Now, so far, we have always, during the civil engineering studies that you have, during the experience as a structural engineer or a civil engineer that you have, it was always code, code, code. So the problem is, you might follow the code and you may get the performance which was expected. But there are cases that you follow the code and may not get the performance because something might go wrong. There are cases also that you do not follow the code and you may get the performance that you wanted. But all of these cases, the performance is the most important one. No one cares whether the code was implemented properly or not. After the earthquake, the only thing that we care is that life of people have been saved and yet your assets are still the same thing. So performance, performance, performance. In this lecture and in the coming lectures that we were going to talk about different components of performance-based earthquake engineering and performance-based seismic design, we are going to criticize codes a lot, and I'm going to try my best to brainwash you that code is not always the solution and code is not sufficient enough for our current design. So, good performance is not solely dependent on code compliance. Code compliance may not necessarily lead to good performance. So you might follow all of the clause of the code, but earthquake strikes and you might not get the performance that you expected. Remember this, we're talking about specific official codes that exist, like ASCII 41, Eurocode 8, Eurocode 3, all of the Eurocode families, New Zealand code, Japan code, Turkey code. What is important for us is good performance. We want our structure to survive and save the human lives which are occupying it. So, on the other side, good performance is not solely dependent on code compliance. So, let's see some examples of these. This is the 2017 Central Italy earthquake. Number of cities were affected, a relatively medium magnitude of 5.7. Unfortunately, 34 people have lost their lives. But although the magnitude was low, the energy release was low, lots of other effects like depth, soil type, distance has affected an intensive or severe shaking in majority of the locations. So the intensity was 8 in Mercalli scales. You can see lots of buildings have been damaged. A lot of these buildings were compliant with the Italian code. Italy is famous for its code. They have had lots of earthquake events before, so the design of those buildings were properly based on what the code needed. But as you can see, we have cases which have damaged. Okay, so look at these projects. They're extremely old, like one of these 2600 before Christ, so nearly 4,600 years old. Earthquakes has happened in Egypt, earthquakes has happened in Iran, earthquakes have happened in Mexico, and earthquakes have happened in Italy. But still, all of these buildings are intact. There wasn't any code at that time, but they managed to, first of all, gather their experience. They had very good engineers, initial engineers, and they realized ways to make sure that the performance of these buildings are acceptable and they don't get damaged during earthquakes. Fun fact, this is one of the initial examples of a base isolator. So whenever the earthquake was striking, all of these rocks which are on top of each other were sliding on top of each other. This was dissipating the energy. This was acting like a damper, like a base isolator, and it was getting this bit, the ground, away from the actual structure. So the structure stayed intact. It's actually the grave of Cyrus the Great. Yes. So, going back to the concept that code is not the best thing, I'm sure we all remember the behavior factor that we were considering it as a discount code, and in the previous lectures we have talked explicitly about it. We said that for stiff or short structures which have lower periods, we will use a lower number of Q factor. For taller and more flexible structures which have higher period, we will use a bigger behavior factor, which was equal to the ductility coming from the ductility factor that we can calculate. So you all know about this, but again, now considering that, is that really the case? Do we really consider all the steel buildings of certain height the same behavior? Is it correct? On another note, do you remember we were taking the total base shear, getting it from that acceleration that we got from the design response spectrum? We multiplied it by the mass and then we divided it up to the floors in a lateral two-dimensional view. Is that really correct? Is it correct that we do a linear elastic analysis but with just the lateral loads, with a simplified base shear? And still the owner will have that question: what happens if a certain magnitude earthquake happens? How my building will perform? And on the other side, when you follow the building code, the only thing that the owner will see is the sign of the design engineer as well as the sign of the council that yes, this building complies and adopts the national building code. But that's it. Nothing else. He won't have a good idea of that. Okay, let's say an earthquake happens, my building doesn't collapse, but is heavily damaged. How long does it take for my building to go back to its normal position? Can I repair it? What will happen to my residents? How much money will I lose just by the damage, and how much money I should spend to repair my building? So all of these were questions that unfortunately the building codes weren't able to answer. So having all of these, the first generation of performance-based earthquake engineering methodologies were introduced, as we discussed, during the years of 2000. This is San Francisco. This is the Fremont Tower built by Arup. This is one of the buildings which performance-based earthquake engineering and performance-based seismic design has been implemented in it. It is in San Francisco, heavily seismic, so we'll see more cases of these in the coming slides. Before we carry on with the first generation, we have to know some, let's say, institutions and organizations which help developing these standards, help developing these guidelines, and help developing these methodologies. Some of these were funders, meaning they provided the research fund for these to carry on. The most important one is FEMA, is the Federal Emergency Management Agency of America. Whenever there is a disaster, a flooding, a hurricane, or an earthquake in America, for sure you have seen their signs and their facilities, and the aid is mainly done by FEMA. They were established in 1979 with an annual budget of about $18 billion US, based on the data from 2018. To just have a comparison, the American Red Cross has about $4 billion US. So FEMA is an extremely big organization, extremely powerful, extremely wealthy, and after a while they realize prevention is the best solution. So they have started gathering researchers, funding them, guiding them, helping them, and coming up with guidelines to give it to the stakeholders and owners to build their buildings to be resistible against hurricanes, strong wind, flooding, as well as earthquake. Another institute to consider is the American Society of Civil Engineers, or ASCE. They were established in 1852. Relatively very old institution. They are kind of equivalent to the Institute of Civil Engineering in UK, but they're in charge of the publication of the codes as well. So America isn't like Europe that it has one unified code. America has different codes, and whichever you follow it and can be applied, it's fair enough. The example that we have here is the design loads on structures during construction. This is something similar to Eurocode 1, which deals with the loading of the buildings. Another institution which works underneath FEMA is NEHRP, or NERP, National Earthquake Hazards Reduction Program. So a lot of work which purely relates to earthquake is done by this institution, which compose of different universities and research groups. So we will be having and referring to FEMA, ASCE, and NERP in the coming slides. So just remember that these are governmental or non-governmental associations. Another organization to consider is PEER. You have already heard of them in different researches. So they are the Pacific Earthquake Engineering Research Center. They are composed of a lot of universities and research institutes, mainly from the west coast of America, where the earthquake is a major issue. So let's see how they define themselves. So yeah, the engineer that you saw at the end, Farzad Naim, is a world famous earthquake engineer, and he has a very good book on basics of earthquake dynamics. You can find the references online, so have a look at that book. It's a good introduction to earthquake engineering with a very simple language. Now that we talked about FEMA, ASCII, NERP, another institute that you have to consider is the Applied Technology Council, ATC. Some of the codes of America are done by ATC. For example, ATC 40 is a proper design code for concrete buildings. Now, out of all the references which relates to this latest performance-based earthquake engineering, there are 4 that you have to know about them. The first one, or let's say the oldest one, is HAZUS, MH. The MH stands for multi-hazard, and it was published in like mid-90s in different years. So it deals with regional loss estimation, multi-hazards, earthquake and other hazards as well, and it is mainly allocated for United States. It was one of the first approaches of analyzing building as a nonlinear model and seeing how much damage they get. So we still refer back to them, and it's a very useful resource. Another reference is FEMA 356, extremely important. It was with the introduction of performance-based earthquake engineering. This publication has pre-standards and commentaries for seismic rehabilitation, which relates back to that performance criteria. This is one of the main references for structural vulnerability and resilience as well. Another extremely important source that our lectures are mainly based on it as well is FEMA P58, which is simply the performance-based seismic design, was published in 2013, and also ASCII 41, the seismic rehabilitation of existing building, is kind of a new version of FEMA 356 with another approach. You can see that these FEMA, ASCII, and ATC and NERP are always collaborating with each other, and there are different names and different codes of them. So as an earthquake engineering, always remember HAZUS, FEMA 356, FEMA P58, and ASCII 41. These are very important references, and you will be using these throughout your design and assessment. Now, having an introduction to what organizations dealt with this PBEE, let's go to the first generation of performance-based earthquake engineering, which was mainly based on FEMA 273, which was one of the first generations, FEMA 356, and ASCII 41, the version 2006. I'm sure you all know this curve, base shear versus lateral deformation. Consider this like roof drift, for example. This is the simple static pushover curve that we always had. This is for the entire building, not component based, for the entire building. Exactly what you can do with softwares like OpenSys and Seismostruct. You build the building either in 2D or 3D, and you start pushing it in one direction, and you record how much base shear resistance the building has versus how much any point of your building is moving. This can be the top floor, for example. Now, looking at this, we can allocate a building situation and a building performance to at any point of it. For example, imagine in the best situation where the deformation is low and the base shear is low, the jaws bar is fully operational, no problem. This happens if, let's say, jaws building has 50 years of lifetime, the frequency of earthquake is 50%. In this 50 years, there is a high chance of a very small earthquake to occur. Remember, the higher the chance of the earthquake is, the lower its intensity and the lower its shaking is. So an earthquake might happen, 50% chance, in this 50 year that this building is going to exist, let's say, and it will perform very well, no problemo. It might even kind of reach to its yielding point, so there is no permanent deformation. Then we increase the earthquake, so the force, the base shear is increasing a little bit. We will see a little bit more deformation, so we are still in the operational region, but there will be a little bit more permanent damage, so we might need to fix some stuff after the earthquake. But still, our event is just 20% chance in the 50-year lifetime of our building. So we are still kind of here between this and this building. Now we move on to higher demands, higher base shear, higher forces, which can cause proper permanent deformation to my building, and permanent deformation is always equal to proper damage. So now we are in rare events, that 10% probability of an earthquake happening in the 50-year lifetime of the building. This 10%, if you can remember, is equal to that 475-year return period for an earthquake. So every 475 years, there is a chance that an earthquake of that magnitude will happen. We call it a rare event. It's not that much. The building will go under some considerable, let's say moderate to extensive damage. It is repairable, and to a certain extent, people have the time and capability to leave the building. After people left the building safely and they saved their lives, the building is not operational anymore. So we have moved from this boundary of operation to life safety. So the building is performing only in a way to save the lives of its occupants and give it enough time for them to leave the building. It will not collapse on their heads, but it will not be functional and operational after the earthquake has finished. So you cannot get back and have your beer and the food. So we are still in this case. Now let's increase the load. We are now permanent deformation. We're increasing the deformation. We're increasing the base shear. We are seeing kind of a plateau. There is now structural instability. It's extremely dangerous. If there is anyone trapped in it, there is a chance that they might have a major injury. And we are in, let's say, in the order of very rare events, 2% in a 50-year lifetime of the building. We can reach to proper collapse as well, but let's say our structure is having extensive damage. It's not collapsed yet, but there is a high chance that it might get collapsed as well. So we call it the structural instability. Again, this is a pushover curve of the entire structural system, looking at its behavior. Any of these base shears can be allocated to a, let's say, an intensity of an event. By event, we mean earthquake. We started from very frequent events, which can have very low shakings, to one occasional event, which maybe in the lifetime of the building there is only 20% chance of it. We get to a higher intensities, stronger earthquakes, rare events, which is that 475-year return period, and then we carry on to proper structural instability under very rare events, 2% chance in 50 years lifetime. So the first generation was saying that, okay, I will allocate such a performance to every single building. I will analyze it in a way that I can tell you at different stages what is the performance of your building and what is the functionality of it. Is it operational, if it's life safety, or is it structural instability and collapse? Based on the first generations, in order to define these, let's say, damage states, they define some damage limit states. Fully operational, immediate occupancy, life safety, and collapse prevention. You can see fully operational, negligible impact on the building, no need of repair, everyone can get back to the structure afterward, everyone happy. Immediate occupancy, you can see the lights are off, but still the building is safe, and it is possible that after a little bit of cleanup and repair, everything goes back to fully operational situation. Life safety was a little bit serious. This is where stuff can get dangerous. Building is safe during the event, yes, so we still are safe and occupants have enough time to get out of the building in a safe let's say, state, but we need proper repair, and it is not easy to get back to fully operational. It will take some time, it will take some money to repair and bring it back to its operational situation, the best case. And collapse prevention is a little bit one step before collapse. Building is on verge of collapse and probable total loss, so either collapse or a little bit before that, and there is a high chance that due to the amount of permanent deformation, you cannot repair it anymore. In these cases, you have to demolish the entire building and rebuild it. So just have these definitions of damage states in your mind for now. Fully operational FO, immediate occupancy IO, life safety LS, and collapse prevention CP. We are going to discuss about these damage limit states, which are mainly based on FEMA 356 and FEMA 273 throughout this lecture, but later on we will introduce some new damage limit states and we will see how we use them.